capture happens, what is the change happening in that particular nucleus that it is leaving gamma ray, or it is scattering gamma ray. What is the change happening in the nucleus?
Proton changes to
Into
neutron or
more
neutron
stable
changes.
state.
Just think about that. If I can excite a ground state nuclear state to an excited state by gamma ray, when I can get a gamma ray out of it?
Sir, when they
Like
when
we'll
they
get a more
ground
stable
state, sir.
state of the
Yes.
element.
So that means it has to be an excited state nuclear state, and it should come back to ground state, and what it will release? Gamma ray. Okay. So it is nothing but very similar to fluorescence. If you want to see fluorescence, right, what do you need to have? You have to have electronic state in the excited state. When it comes back to the ground state, it releases the light in the form of fluorescence. Similarly, I want to have a gamma ray coming out of a nucleus. When I can have it? What all of you are saying is correct. I have to put an electron. I can even put a proton. Proton is very hard to put that inside a nucleus. Electrons are easier. Beta ray, even alpha ray, I can push that in a system and make it unstable. When I'm talking about that, you actually know these terms, that we actually need to put an unstable or metastable nucleus. But you have to connect it with the Mossberg now. What you are actually creating, an excited state of a nucleus, which actually not very stable. Now it's coming to a ground state. And when it's coming to the ground state, it is releasing a radiation, which is nothing but the gamma. Okay. So to summarize that, what I'm saying, that if you want to create a gamma ray, to make sure that one of the ground state of a nucleus go to the excited state of the nucleus, you have to do the opposite first. You have to create an excited state of a nucleus first, which is unstable or metastable, and which will come down to the ground state, and in the condition, it will create a gamma ray. Okay, that is how we create gamma rays. We'll go into that in more details in the next class, that how we actually create the gamma ray. But today you get the gist of it, how I can create a gamma ray by making a system where a excited state nucleus, unstable system. Okay, so an unstable excited state, it is going to release the energy in the form of gamma ray. And now say I am using the same nucleus. Say I am using iron 57 nucleus, and similar iron 57 nucleus is over there sitting in the ground state. So what will happen? This gamma ray will come and excite this ground state to my excited state. And if it happens, what I can say, I am actually exciting a ground state iron 57 to an excited iron 57, and during that I will absorb that energy, and this nuclear state change will happen. Right? So that is what I am trying to do. Again, question comes, why do I need to do that? Because I am actually exciting a iron first, making it come to the ground state, and the same gamma ray, it is getting absorbed by the similar looking iron and going to excited state. So what is the full point of that? The point is that this iron system and this iron system may have the same nucleus, but they may differ what is there in the surrounding. What is the actual oxidation state? What is the nucleus? What is the electronic spin state? High spin or low spin? That might differ. So over here, the nuclei looks pretty much similar, but what can differ is the surrounding or the electronic state. And as we just discussed in the beginning of this page, that the electrons can also affect the nucleus. So there may be a subtle change in the energy state of the excited state or the ground state. And that change, if I can monitor with the change over here, I will come into that how we are going to do the change. But what I can see, that whether this gamma ray energy is sufficient to do this transition, or I have to adjust it a little bit so that it can do the resonance and give me the idea how much is the ground state change, how much is the excited state change. And if I can get that idea, I will have an idea of how the electronic state is affecting my nucleus. Coming back one more time, what I am actually doing, I am getting a gamma ray first from a excited state of the same nucleus, say iron 57 we are talking about. iron 57 excited state coming back to the ground state, it is leaving a gamma ray. That gamma ray is absorbed by a similar iron 57 nuclei. Similar nuclei, but not similar electronic environment. Due to this electronic environment different, the ground state and excited state may differ a little bit. Over here, my goal is to capture that particular difference. And if I can get that particular difference, I can have an idea how this electronic state around this absorber molecule is getting affected. And from there, what are the things I can say? I can say about the oxidation state. I can say what is the environment around, what is the spin state of the system. By spin state means high spin or low spin system. All those things I can have a very clear idea by this spectroscope. Okay, so that is why we are looking into nuclear state transition, because through the nuclear state transition, what I am actually going to get into what is happening around that nucleus. That means in the electronic systems. Okay, any questions up to here?
So subtle change means, or what do you mean?
We'll come into that. What do I mean by subtle change?
And on questions, as you know that there is a approximation known as Born-Oppenheimer approximation.
Very good.
And that approximation tells that you can that approximation tells that, as far as I remember, that nuclear coordinate cannot be interact with electronic coordinate. So that's why you write the wave function as psi equal to psi 1 into psi 2, and that's why you can write energy equal to E1 plus E2. It's not it. And
Yes.
here actually it happens. Nucleus can interact with electronic cloud, and electron cloud also get interaction by nucleus. Is not it, but
Yes.
I can actually correlate these two things, Born-Oppenheimer
Yes.
approximation here, and
Yes.
yeah, I think you
Yes.
got my question.
Yes, I got the
Yeah,
question.
yeah,
So let me reiterate that. So how this electronic and nucleus interaction is actually happening. So there, let me clarify what the Born-Oppenheimer principle is. So anybody else want to tell me what is a Born-Oppenheimer principle? Annesha, are you there? Okay, Annesha is not there. So Rajeshwari, can you tell us what is a Born-Oppenheimer principle?
During electronic transition, the nucleus does not move, if I put
Yes.
it simply.
Yes. So that is probably the easiest way you can think about Born-Oppenheimer principle, which says that when I'm exciting an electron, then the nucleus doesn't change its position. Okay, it remains as it is. So what it is saying, you have to understand properly that over here, what is the state I am changing? I'm changing the electronic state. And what is the energy required for the electronic state change? For an electronic state change, I need the energy in the form of UV visible region. So obviously the nucleus is not going to change for two different things. First, the nuclear state change requires much more higher energy that I'm not giving. And secondly, you have to concentrate on the term movement, because nucleus is not static, it is also moving. But the time scale at what the electron is actually moving from ground state to the electronic state, that means the time it requires to reorient itself from the ground state distribution to electronic distribution, it happens in femtosecond. And within this femtosecond, the nucleus is not moving at all. Okay, so that is the Born-Oppenheimer principle is. And why it is important? Because during the calculation of this quantum mechanical calculation, I can get rid of the nuclear part altogether and think about the electronic state change. Okay, now what is I'm talking about in Mossberg spectroscopy or nuclear state change? First, what is the energy I am giving? I am giving the energy of gamma ray. That means I am changing the nuclear state actually. Okay, so during the nuclear state change, this nuclear state change is also happening, but between that, is there any rearrangement of the electron? Is it also happening at the same time? Yes, it is happening at the same time. And over there, we cannot say that electronic state change is independent of the nuclear state. The other way may not be true, but this is a different way we're talking about. We are changing the nuclear state altogether. And when the nuclear state is getting changed, the electron might get redistributed. For an example, the electronic distribution around a I equal to 3/2 and I equal to half may not be the same. And that is what I'm trying to catch. That is it same or different? If it is different, can I catch it? And if I can measure it? And say, I'm saying you, yes, I can measure it. But the confusion you have with the Born-Oppenheimer principle, the Born-Oppenheimer principle is for the electronic state change. Over there, nucleus is not changing at all because I'm not changing the nuclear state at all. The delta I is 0. What I'm changing only the electronic state. And over here, I'm changing the nuclear state itself. A nuclear state, as it requires more energy, obviously it is affecting the electronic state. Does it clarify your thought a little bit, some of them?
Okay.
Yeah, if you have still doubt, clarify.
The thing I understood that in mass spectroscopy, we are bothered very much about nuclear state, and that's
Yes.
why electronic distribution automatically come into play.
Yes.
And
Because
and
just think in this way, if I change the electronic state, does it going to affect too much on the nuclear state?
yeah, that's
It's not.
that yeah.
But if you change the nuclear state, is it going to affect the electronic state?
Yeah, absolutely.
So that is what you are actually changing. You got the point?
That's why here
Born-Oppenheimer
principle is not valid.
Not valid because Born-Oppenheimer principle is for the electronic state change.
Okay.
Okay, and over here, what we are changing is the
nuclear state.
nuclear state. So that way, it is not really matter. Okay.
Okay, so thank you, sir.
Anyone?
And
more
one more
questions?
question, sir.
Yes. Please go ahead.
Yeah. And I have the one more question. This example we mentioned about the iron 56 in ground state and iron 56 in excited state. They have different electronic environment, different nuclear spin state, different nuclear spin state, and their iron 56 energy is different from iron 56 NRM excited state. Is there any name between them? Means
Yes, there is a name between them, and there is a name of this particular effect, but we'll cover that in the next class. To know that this is actually known as a parameter, and that is the important parameter for Mosbach spectroscopy. But we'll come into step by step. Okay, first we have to follow that what is actually logically actually have to create our logic first, that actually what is actually happening, and then slowly will come what is that called. And I actually haven't answered that. We actually give you just the fact that yes, the electronic state can affect the nuclear state. Question is why and how. Okay, that is I'm not giving the answer right now. I'm just giving you the fact. Yet it does affect. First, we'll cover up how the effect actually works, and then we'll go into the details why the effect is there, why an electron can affect my nucleus. Okay, we'll come into that in the next class. So in today's class, we are mostly looking into how this effect actually works. Okay. Any more question up to here? Otherwise, we'll go forward. So now we are talking about electron and nucleus interaction, and this interaction has a particular name which you already learned from the EPR class, which is known as hyperfine interaction. Okay, so this hyperfine interaction is actually what is the factor I'm trying to guess or trying to analyze through this Mosbach spectroscope. So there is a hyperfine interaction that is obvious. You know from the other way around in the EPR. In the EPR, what you say, if you have unpaired electron and if you have a nuclear spin, the nuclear spin affects it. It's split it up. That means the nuclear spin and the electron spin actually interact. Similarly, the thing is that if you have a non-zero nuclear spin state, is it also going to show some effect due to the presence of the electron spin on the other hand side? So that is what we are trying to get. And for that, we have to find out a system where we can actually analyze this